Look at the nearest clock and you are looking at the thing you trust more than almost anything else in your life. Time feels like the one fact that never wobbles. It moves. It moves forward. It carries you from this morning into this evening, whether you want it to or not, and it has never once in your entire life run the other way. Yet here is the strange truth that physics has been quietly holding for more than a century. Every fundamental equation we have ever written down works perfectly well if you run it backward. Newton's laws of motion do not care which way time flows. Reverse the direction of time inside them, and they still describe a real, valid, physically allowed process. Maxwell's equations for light and electricity behave the same way. So does the Schrodinger equation, the master rule of the quantum world. So do Einstein's field equations for gravity itself. In the deep mathematics that underlies everything you have ever touched, there is no rule that says time must go forward. Picture a coffee cup slipping off a table. It hits the tile and shatters. The sound is sharp, the pieces scatter in 100 directions. A little warmth and noise spill out into the room. Now imagine that footage running backward. The shards lift off the floor, gather themselves silently out of the air, and settle back into a whole cup on the table, still warm. You have never seen that happen. Not once, not anywhere, not in the whole history of the world. But no equation of physics forbids it. The mathematics is perfectly happy either way. The universe simply refuses. That gap is where tonight lives. Not the gap between what we can build, but the gap between what our laws allow and what the world actually does. Before we go deeper, a small thing. If you find this quietly fascinating, a like or a subscribe helps this channel more than you would guess. And these scripts play on Spotify too if you drift better with just the voice. That is the whole ask. Now settle in with the question and let it turn slowly. The question sounds childish until you sit with it. What is time actually made of? You would think physics, of all things, would have a clean answer. It does not. And the reason it does not is far stranger than a missing fact. It is that time was never something physics figured out. Time is something physics assumes before it can begin. Think about what an equation of motion is. It tells you how something changes from one moment to the next, where the planet will be a second from now, how fast the wave will travel, what the particle will do in the next instant. Every one of those sentences already contains time inside it. You cannot write down how something changes over time without already having time to change over. Physics does not derive time from anything deeper. It reaches for time first, lays it down like a table under the experiment, and only then starts doing the work. So when you ask a physicist what time is, you are asking them to explain the one thing their equations were built on top of. It is the floor of the room, and the floor is very hard to see because you are standing on it. The ordinary picture in your head is probably a river, time as a great current, flowing at the same steady rate everywhere at once, sweeping the entire universe along together from past to future. One shared now, moving forward for everyone, for every star, for every atom, all in step. It is a beautiful picture. It is also, as far as physics can tell, wrong in almost every part. There is no single river, there is no shared rate, and there may be no flowing at all. Most people, when pressed, reach for a better answer than the river. They reach for a word you have heard before, entropy. Time moves forward, they say, because things fall apart. Heat spreads out. Order decays into disorder. Ice melts. Milk mixes into coffee. Buildings crumble, and none of it ever runs backward on its own. That direction, from order toward disorder, is real, and it does point one way. Physicists call it the arrow of time, and it is one of the sturdiest facts we have. But look closely at what that answer actually says. Entropy tells you which way time points. It does not tell you what time is. Those are different questions, and mixing them up is one of the oldest mistakes in the subject. Saying time is entropy is a little like saying a river is the direction it happens to flow. The direction is real. It is not the same thing as the water. Entropy explains the arrow. It does not explain the existence of the thing the arrow is stuck into. So we are left in a genuinely uncomfortable place. Our equations do not define time, they assume it. Our best everyday answer, entropy, explains time's direction but not its being. And this is where physics, instead of getting firmer, starts to dissolve under your hands. Because a small group of serious physicists have begun to suspect that time is not a basic ingredient of reality at all. The idea has a name, the thermal time hypothesis. It was developed by the physicist Carlo Rovelli and the mathematician Alain Connet, and it turns the whole question inside out. In their picture, time is not woven into the fabric of the universe. Time is something that emerges, the way a crowd emerges from people, the way a wave emerges from water. And the thing it emerges from is not more time, it is our own ignorance. Consider temperature for a moment, because it is the clearest way in. Temperature feels fundamental. A thing is hot, a thing is cold, and you can feel the difference on your skin. But temperature is not a basic ingredient of the universe. There is no temperature inside a single atom. Temperature is a statistical story we tell about huge numbers of atoms jostling and colliding, too many to track one by one. It is what the average motion of a countless crowd feels like from the outside. It is real, and it is emergent. It comes from the fact that you cannot follow every particle at once. The thermal time hypothesis says time might be exactly like that. Underneath, there is a system of quantum states with no time in it, no ticking, no flow, no before and after. And time, the passage you feel right now, emerges as a statistical effect from the fact that you can never know that underlying system completely. Your ignorance is not a flaw in the picture. Your ignorance is where time comes from. The mathematics behind this is drawn from a deep result called the Tomita-Takasaki theorem, and it links the flow of time to which thermal equilibrium state a system happens to be in. Change the state, and you change the very rate at which time flows out of it. If that sounds like an abstraction, notice where it touches the real world. This same family of ideas connects to the Unruh effect, the strange prediction that an observer accelerating through empty space would feel that empty space as a warm bath of particles. It connects to Hawking radiation, the faint glow that black holes are thought to leak as they slowly evaporate. Warmth and time in these pictures turn out to be two faces of the same underlying thing. And in the boldest version of the idea, the universe as a whole can stay perfectly timeless, while its pieces come alive with time through quantum entanglement. Time becomes a relationship between parts, a shared history bundled together, rather than a river running past all of them at once. Sit with what that means. It says the universe might not have a when built into it. Not a slow when, not a hidden when. No when at all, at the bottom. And everything you call the passage of time, every moment that has ever felt like it was slipping away, would be warmth rising off a structure that itself never moves. You do not have to accept that to feel how far it is from the river in your head. And it is not even the strangest position on the table, because among physicists who take time seriously, there is an old standoff, and both sides are reading from the same equations. On one side stands the block universe, sometimes called eternalism. It grows straight out of Einstein's relativity, and many physicists regard it as the honest reading of what the theory says. In the block universe, the past, the present, and the future are all equally real. All of it exists, laid out together as a single four-dimensional block of space-time. Nothing is uniquely happening now. There is no special moment the universe is currently passing through, because every moment is simply there, printed into the block, as real as every other. Picture the whole of existence as a finished reel of film, with every frame already exposed, every explosion, every heartbeat, your own birth and your own death, all printed at once, motionless, complete. Nothing on that reel is moving. The now you feel is just wherever your attention happens to be shining its light. Slide the light forward and you call it the future. Slide it back and you call it the past. But the reel itself does not flow, any more than a road flows past a map lying still on a table. In this picture, time does not pass. It just is, all of it, forever. That idea can make the back of your neck cool. If it is true, then this moment, the one you're in right now, is not being created, and it is not vanishing. It is a fixed frame that has always been there and always will be, and so is every moment you have ever grieved as lost. Across from the block universe stands the opposite camp, presentism. Here, only the present is real. The past no longer exists. It is gone, evaporated into nothing. The future does not exist yet. It has not been built. There is only this thin, moving edge, this single instant, and it is the whole of what is real. Everything else is either memory or expectation, and neither of those is a place. The physicist Julian Barber pushed this further than almost anyone. In his 1999 book, whose title alone should keep you up, called The End of Time, he argued that time as you experience it is fully an illusion. His argument is unsettling in how simple it is. What evidence do you actually have of the past? only a memory, and that memory is a pattern sitting in your brain right now, in the present. What evidence do you have of the future? Only a belief, and that belief is also here, now. You never touch the past directly. You never touch the future. You only ever have this instant, holding traces that point outward in both directions. Strip those traces away, Barber says. There is no flowing river left. There are only nows, each complete, each still. So picture the two of them arguing in the same room. One physicist insists that only this instant is real, that everything else has either dissolved or has not yet come into being. The other insists that nothing has ever been more real or less real than anything else, that all moments simply exist together. They disagree about the deepest possible fact, whether the past and future are real at all, and they are both working faithfully from the same equations. The mathematics does not settle it. The mathematics allows both. That is the position physics keeps arriving at whenever it turns and looks straight at time. Not a clean answer with a few loose ends. A subject that gets less solid the harder you press it. Every definition it reaches for slips. Time as a river fails. Time as entropy explains only the arrow. Time as a fundamental ingredient may be a mistake, warmth mistaken for water, and time as the flowing now may be a trick of attention playing across a block that never moves. Here is the beat to carry with you as you drift. It may be that physics does not merely fail to define time. It may be showing us something far stranger. That time is not written into the foundations of reality at all, but leaks out of a deeper, timeless mathematics, the way warmth leaks out of a crowd of jostling atoms that individually have no temperature at all. The universe underneath may not have a clock. The clock may be us. And yet, whatever time turns out to be, one brute fact refuses to move. The cup shatters and never reassembles. You remember this morning and not this evening. By the end of tonight, we will have followed that one stubborn direction all the way down to where it comes from, and it will lead somewhere you would not expect. The laws do not care which way time runs. The world does. Something has to break the tie between them. So before you can ask why time only moves forward, you have to look at the one direction it never runs backward. So before you can ask why time only moves forward, you have to look at the one direction it never runs backward. Here is the rule at the center of it. In an isolated system, entropy can only stay the same or increase as time goes on. It never decreases. Entropy is a rough measure of disorder, of how many ways a system's particles could be rearranged and still look the same to you, and that quantity in any closed box only ever climbs. Rudolf Clausius wrote this down formally in 1865 and called it the second law of thermodynamics. Ludwig Boltzmann gave it a deeper meaning in 1872, showing that entropy is really about counting arrangements, and in 1928, the astrophysicist Arthur Eddington gave it the name we still use. He called it the arrow of time. Think of a wine glass shattering on tile. The sound is sharp. Glass scatters into hundreds of directions. Heat and noise radiate outward into the room. Now imagine running that same footage backward. shards lifting off the floor, sound waves gathering out of the air, the pieces rising and knitting themselves silently and perfectly back into an intact glass sitting on the counter. You have never seen that happen. Not once, not anywhere. And here is the part that should stop you cold. Nothing in the fundamental laws of physics forbids it. That is the deep puzzle, and it is worth sitting with slowly. Every microscopic law we have is time reversal symmetric. Newton's laws of motion, Maxwell's equations for light and electricity, the Schrodinger equation of quantum mechanics, and Einstein's field equations for gravity. Take any one of them, reverse the direction of time in the mathematics, and you still get a perfectly valid physical process. The equations do not care which way the clock runs. They describe the glass reassembling just as happily as they describe it shattering. At the level of individual particles bouncing off one another, forward and backward are equally legal. So where does the arrow come from? If the rules that govern every atom are indifferent to direction, why does the whole world you live in point so relentlessly one way? The answer that most physicists give traces back to Boltzmann, and it is a strange and beautiful idea. The arrow of time is not written into the laws at all. It is written into the beginning. It lives in what physicists call the boundary conditions, the starting state of everything. The universe began in an extraordinarily low entropy, extraordinarily ordered condition, and everything that has happened since is simply a long, slow drift away from that improbable start. Physicists have a name for this assumption. They call it the past hypothesis. The reason time seems to flow forward is that it is flowing away from a beginning that was tidy beyond imagining, toward a future that has vastly more ways to be messy. To feel why that matters, picture a box of puzzle pieces. There is exactly one arrangement that makes the finished picture, and there are billions upon billions of arrangements that leave the pieces jumbled. So if you shake the box, jumbled is almost always where you land. Order is rare, disorder is common, not because anything pushes toward disorder, but because there is so overwhelmingly much more of it. The universe shakes the box every instant, and the pieces drift, and the drift is what you feel as the passing of time. Now, how ordered was that beginning? This is where the numbers stop being ordinary. The physicist Roger Penrose set out to calculate it. He compared the volume of possible universe arrangements that would look like our universe today to the vastly larger space of arrangements that would look like the state the universe actually started in. He arrived at a figure for how special that starting point was. The odds against the universe beginning in the low entropy state it actually began in are about 1 in 10 to the power of 10 to the power of 123. Let that settle, because ordinary language cannot hold it. That is not 1 in a trillion. It is not 1 in a trillion trillion. It is 1 followed by 10 to the 123 zeros. And here is the way to feel the size of it. There are roughly 10 to the 92 subatomic particles in the entire observable universe. If every single one of those particles were itself a zero, written down on the page, you would still not have anywhere near enough zeros to finish writing the number. You would run out of matter long before you ran out of digits. That is the improbability of the tidiness we were born from. And there is a twist inside this that surprises almost everyone, because it involves gravity, and gravity keeps the entropy books in a backward way. Most systems, left alone, spread out toward uniformity, and uniformity is their high entropy state. Think of milk stirring evenly through coffee. But gravity does the opposite. Gravity has what physicists call negative heat capacity, which means a cloud of matter, when it clumps together, gets hotter and more spread out in the ways that count, not less. So for gravity, a smooth, uniform, evenly spread universe is actually the low entropy state. A clumped universe, full of dense knots and black holes, is the high entropy one. This is why the smooth early universe was so special. The Big Bang was not a chaotic explosion in the way the word suggests. Gravitationally, it was almost perfectly smooth, and that smoothness was exactly the rare, ordered, low entropy condition that gave the universe somewhere to go. Because matter could then slowly clump under gravity, stars could ignite, galaxies could gather, planets could form, and eventually you could exist to wonder about any of it. The reason there is a story to tell at all, a sequence of before and after with stars and life in the middle, is that the beginning was smooth in a way that let entropy rise instead of already being maxed out. A universe that started clumpy and dead would have had no arrow worth the name. There is honest disagreement here, and it is worth naming. Not every physicist accepts that the beginning had to be quite so uniquely improbable. A 2016 analysis in the journal Physical Review D argued that you might not need the past hypothesis in its strongest form at all. The reasoning is that almost every possible cosmological starting state expands as time goes on, and the sheer fact of that expansion can drive entropy upward locally, without requiring one single, staggeringly special initial condition. It is a genuinely contested alternative, and the question of exactly why the beginning was the way it was remains open. But whichever version you favour, the world still only runs one way, and that one way traces back to conditions at the start, rather than to any preference buried in the laws. Now bring this all the way home into your own skull, because the arrow of time is not just out there in shattering glasses and cooling stars. It is the reason you have a past at all. Ask yourself why you can remember yesterday but not tomorrow. It feels too obvious to question. Of course, memory points backward, but nothing in the equations demanded that. The direction of memory is another consequence of the second law, and the logic is quietly astonishing. Consider what it takes to record a memory, to lay down a memory in a brain, or to write a file onto a hard drive. You have to physically change the state of that system. You have to burn energy, release a little heat, nudge molecules into a new configuration, and every one of those acts increases the entropy of the world around you. Recording is not free. It always leaves the universe a little more disordered than before, which means a memory can only ever be written in the direction that entropy is increasing. You can only accumulate records of the lower entropy past, never of the higher entropy future, because the very act of recording is itself one of the steps in entropy's climb. Your memory points backward for exactly the same reason ice melts and never unmelts. They are the same arrow, seen from the inside, and we can now point to where in the brain that ordering seems to live. Brain imaging research has traced the way humans sort events into past versus future to activity in the hippocampal formation. That is the same deep structure responsible for memory in general and for navigating through space. The part of you that knows which way is home in a hallway is bound up with the part of you that knows which way is yesterday in time. Somewhere in that fold of tissue, the thermodynamic arrow of the whole cosmos gets translated into the simple, felt certainty that what is done cannot be undone. So step back and look at what one fact carries. The reason you can remember your childhood but not your death. The reason a puddle never gathers itself back into an ice cube on a warm floor. The reason coffee never unstirs and smoke never pours back into the cigarette. The reason the universe has a past at all, a settled and finished behind that differs from an open and unwritten ahead. All of it traces to a single circumstance, roughly 13.8 billion years ago. The universe began in a state so improbably ordered that its odds were about 1 in 10 followed by 10 to the 123 zeros, and everything you call the flow of time is the slow, irreversible, unstoppable spending of that original tidiness. There is a kind of vertigo in it once you see it clearly. The forward march you have trusted your whole life, the current that carries every moment into the next, is not a law handed down by the deepest physics. The deepest physics shrugs and says either direction is fine. The march is instead an inheritance, a momentum given to us by a beginning we did not choose and cannot fully explain. Time has a direction only because it started somewhere clean and has been getting untidier ever since, and it will keep getting untidier for as long as there is any order left to spend. The strange part is that nobody set out to discover the direction of time. They set out to understand heat. In the middle of the 1800s, engineers wanted to know why a steam engine could never be made perfect, why some part of the fire always slipped away, wasted, no matter how carefully the machine was built. The answer, when it came, turned out to be about far more than engines. It was the first hard clue that the past and the future are not the same kind of thing. The man who found it was a German physicist named Rudolf Clausius. In 1865, he gave the missing quantity a name. He called it entropy, from a Greek word for transformation, and he stated a law about it, short enough to fit on a coin. In an isolated system, entropy tends toward a maximum. Heat flows from hot to cold, and never the other way on its own. That was the second law of thermodynamics, written down clearly for the first time. Notice what Clausius had really done. He had given disorder a name, and he had given it a direction. Before him, the equations treated time as a smooth road you could travel either way. Clausius drew an arrow on that road. He could not yet say why the arrow pointed the way it did. He could only say, with quiet certainty, that it always pointed the same way. Entropy climbs. It does not fall. The clue sat on the table, waiting for someone to explain it. The someone was an Austrian named Ludwig Boltzmann. In 1872, he took the quantity Clausius had named and asked a deeper question. What is entropy actually made of? His answer changed the shape of the whole puzzle. Entropy, he argued, is a matter of counting. Count all the ways the atoms could be arranged while the thing still looks the same from outside. A tidy, ordered state has very few. A jumbled state has an almost unimaginable number. The world drifts toward the jumbled simply because there is so much more of it to drift into. That was the first real basis for telling past from future. Not a new force, not a hidden hand pushing the world along. Only arithmetic, applied to atoms far too many to ever track one by one. The past was the direction with fewer arrangements. The future was the direction with more. Boltzmann had located the divide between them, and he had located it in the counting, not in the laws. But his answer carried a problem inside it, and his critics saw it at once. The laws governing those atoms, the ordinary laws of motion, run equally well in both directions of time. Reverse every particle along its path, and nothing in the mathematics complains. So if the underlying rules show no preference, how can the whole crowd of atoms prefer one direction so strongly? How can time-reversible parts add up to a time-directed whole? Boltzmann's reply was that direction is a matter of overwhelming likelihood, not strict law. The tidy states are so rare, and the jumbled ones so common, that the slide toward jumble is all but certain. Certain, yet never truly forbidden the other way. Only made so unlikely that you would wait longer than the age of the universe to catch it running backward. This was the lonely idea to hold in 1872. Many respected scientists still doubted that atoms were real at all. To them, Boltzmann was building a grand statistical story on top of particles nobody had ever seen. He argued for these atoms for the rest of his life, often against the mood of his own field. He wrote the counting into a single compact equation, one that ties entropy to the number of possible arrangements. Today it is written as S equals K log W. It says, in the plainest terms, that entropy is a measure of how many ways a state can be built. Boltzmann died in 1906, worn down and largely unvindicated. Within a few years, the reality of atoms was settled beyond argument, and his statistical picture became the foundation of a whole science. His formula was carved onto his gravestone in Vienna, set above his name in plain stone. S equals K log W. The equation outlived the man who had fought so hard for it. You can still stand in front of it, a line of physics chiseled where an epitaph usually goes, the clue he found now written in granite. So by the early 20th century the pieces were on the table. Clausius had named the quantity and given it a direction. Boltzmann had shown that the direction lived in the counting of arrangements. What was still missing was a name for the thing itself, a phrase for this one-way current that every clock and every candle and every cooling cup of tea obeyed without exception. That phrase arrived in 1928 from a British astrophysicist named Arthur Eddington. In a book called The Nature of the Physical World, he was searching for a way to describe the strange one-sidedness of time. He wanted a term for the property that has no equal in space. In space you can face any direction you like, in time you cannot. And so he wrote a phrase that has stuck to the physics ever since. He called it the arrow of time. Eddington was careful about what he meant. He tied the arrow directly to entropy, to the one-way increase demanded by the second law. Draw the arrow, he said, in the direction in which disorder grows. That is the only arrow physics gives you. Every other law, he pointed out, works just as well running backward. This one does not. The arrow of time in his hands was simply the direction in which entropy keeps climbing. Look at what these three men had assembled between them. Clausius supplied the quantity and the rule it obeys. Boltzmann supplied the reason, hidden as a counting of unseen atoms. Eddington supplied the name and pinned it firmly to the rise of entropy. Each one added a clue, and each clue pointed the same uncomfortable way. The split between past and future was not written into the deep laws of motion at all. Those laws did not care which way time ran. The split lived somewhere else, in the numbers, in the overwhelming odds against ever finding yourself in a teedy state by accident. And that is where the detective story leaves you with its final, quiet twist. If the future is only the direction with more arrangements, then the past must be the direction with fewer. Follow that thread far enough back and it demands something startling. The universe must have begun in a state of almost impossibly few arrangements, a state so ordered, so rare among all the ways matter could have been laid out, that everything since has been a long slide away from it. The arrow points forward only because it started somewhere so extraordinarily low. The whole one-way character of time, the reason you remember one direction and drift toward the other, rests on that improbable beginning. Clausius, Boltzmann and Eddington had turned a puzzle about steam engines into a statement about the birth of the cosmos. Step by patient step, they had shown that time has a direction, and they had traced that direction back to a single staggering fact about how the universe was set up. That much, at least, they had settled. But direction is only half of time's strangeness, because the rate itself turns out to be something you can bend. But direction is only half of time's strangeness, because the rate itself turns out to be something you can bend. Not in a metaphor, in hardware, in clocks you can buy, in satellites over your head right now, in particles falling through your body as you lie there. The rate of time is a real, local, measurable quantity, and it is different in different places, and physicists have caught the difference over a height of 1 millimeter, about the width of a sharp pencil tip. That is where this part of the night is going. Time is not one river. It is personal. Start with the 2 ways to bend it, because there are exactly 2, and Einstein found both. The first is motion. Special relativity says that the faster something moves relative to you, the slower its clock ticks from where you're standing. Not slower because the mechanism jams. Slower because time itself for that fast thing is running at a different rate than yours. Speed steals from the clock. The closer to the speed of light, the deeper the theft. The second is gravity. General relativity says that a clock sitting deeper in a gravitational field ticks slower than a clock higher up. And the reason is stranger than the first, because in Einstein's picture, gravity is not a force at all. It is the curvature of space-time itself. Mass bends the shape of time and space around it, and a clock nearer a heavy body is sitting in more sharply bent time, so it lags. The floor of a building ages more slowly than the ceiling. Hold those two together, because everything else in this part is those two effects fighting or adding. Motion slows a clock. Depth in gravity slows a clock. And nature runs the experiment for you, constantly in the sky. Consider the muon. A muon is an unstable particle, a heavier cousin of the electron, and it is being made right now, somewhere between 6 and 9 miles above your head. Cosmic rays from deep space slam into the top of the atmosphere and shatter into showers of these particles. The muons come screaming downward at up to 0.994 times the speed of light, almost light itself. Here is the problem. A muon at rest barely exists. Its half-life is 2.2 microseconds, 2 millionths of a second, and half of them are gone. Even moving at nearly the speed of a light, in that tiny sliver of life, a muon should cover only about 660 meters before half of any batch has decayed. A little over 1/3 of a mile, from 6 to 9 miles up. That means essentially none of them should ever reach the ground. They should evaporate in the high air, miles over your head, and never touch the surface of the earth. And yet muons are the main thing raining through you at sea level. They are the primary component of the cosmic radiation that actually reaches the ground. They are passing through your body as you lie there, invisible, harmless, in soft showers, thousands of them, every minute. The particles that should have died miles up are here, at the bottom, in numbers. Time dilation is why. From the Earth's point of view, the muon is moving so fast that its internal clock is running slow. Its brief life is stretched out, extended, roughly ninefold, 9 times longer than a muon sitting still would get, and 9 times 660 meters is enough. Enough to cross those miles of air and land on the detector, on the mountaintop, on you. The particle does not know it is living longer. From its own point of view, its life is as short as ever. It is the geometry between you and it that has changed. This is not theory alone. Bruno Rossi and David Hall measured exactly this in 1941. Counting muons at different altitudes and watching the numbers refuse to fall off the way they should. It is now a standard student experiment, run in undergraduate physics labs every year. Before we go further, one small thing. If you are still awake and this is landing, a like or a subscribe genuinely helps this channel keep making these. We are on Spotify too, for the nights when you would rather just close your eyes and listen. That is all. Back to the strangeness. Because here is what the muon is quietly telling you. Time is personal. It is local. It runs at a rate that depends on how you are moving and where you are sitting. There is no master clock hanging in the sky that everyone shares. Your watch is yours. The muon's clock is the muon's. They do not have to agree, and they do not. Which means the strangest version of this is not out in space. It is in your own body. Right now, as you lie flat, your head and your feet are at slightly different heights above the center of the earth. Your head is a little farther out. Your feet are a little deeper in the planet's gravity. And by general relativity, that means your feet are ticking a hair slower than your head. Your head is aging faster than your feet, not because they are made of different stuff, because they sit at different depths in the curve of time. Over a lifetime, it adds up to almost nothing, a sliver of a second, far too small to feel. But it is real, and it is measured, and it does not switch off just because you cannot notice it. Climb higher, and the effect grows. A clock on a mountain runs faster than a clock at sea level. A clock in a jet high up but moving fast has both effects at once. The altitude speeds it up, because it is higher out of the gravity. The speed slows it down because it is moving. Fly 2 atomic clocks around the world on airliners and compare them to a clock that stayed home, and the flying clocks disagree with the ground by exactly the combined amount relativity predicts. That is the Haffel and Keating experiment, and it worked. The clocks came home carrying slightly different amounts of elapsed time, and the difference matched the math to the microsecond. Now the part that turns all of this from a curiosity into a piece of your daily life. The reason it matters that you understand this is not philosophical. It is that you are using it, probably every day. And it only works because engineers built Einstein into the machine. The global positioning system is a fleet of satellites, each carrying an atomic clock, and the whole thing works by timing. Your phone listens for the ticks from several satellites at once, and works out how far each signal travelled by how long it took to arrive. Distance from time. That is the entire trick. Which means the clocks up there have to be trusted absolutely, and those clocks are caught in both of Einstein's effects at the same time, pulling in opposite directions. The satellites are moving fast in orbit, so special relativity slows their clocks by about 7 microseconds per day. But they are also high above the Earth, out where gravity is weaker and time runs faster, so general relativity speeds their clocks up by about 45 microseconds per day. Add the two together. The slowdown from speed, the speed up from altitude, and the altitude wins. The net result is that each satellite clock runs about 38 microseconds per day, faster than an identical clock on the ground. 38 microseconds, 38 millionths of a second per day. It sounds like nothing. It is nothing to a human. But light and radio travel about 186,000 miles every second, so even a few microseconds of clock error translates into miles of position error. Left uncorrected, the system would not drift slowly and gracefully. Your navigation fix would go wrong within about 2 minutes, and then the error would keep piling up, roughly 10 kilometers per day, over 6 miles a day of drift, until the map on your screen was pointing you into the sea. So the engineers did something quietly astonishing. They mistuned the clocks before launch, on purpose. Each satellite clock is built to tick at a frequency that is deliberately, permanently wrong on the ground. The natural frequency is 10.23 megahertz. They set it before flight to about 10.229943 megahertz. Slightly slow, by design, here on Earth. Then they launch it. And once it is up in the weaker gravity of orbit, the universe's own physics speeds it back up, and it lands exactly on 1023. The clock is only correct when it is in space. Relativity is not a correction bolted on afterward. It is machined into the part in the factory before the rocket ever leaves the pad. The whole global network is a monument to the fact that time runs at different rates at different heights, and it would be useless without it. Sit with that for a moment. Every time a map on a screen quietly knows where you are, you're watching a theory about the shape of time do a job. A theory about clocks running slow near mass, made in 1915, is soldered into the guidance of your ordinary day, and the measurement has gotten so fine that the difference now shows up over distances you can barely see. In February 2020, physicists at JILA, a joint institute of the National Institute of Standards and Technology, and the University of Colorado Boulder, did something that would have sounded impossible not long ago. They took a single sample of ultra-cold strontium atoms, about 100,000 of them, held in a lattice of laser light, and they measured the flow of time across the height of that sample, not across a mountain, not across a jet flight, across 1 millimeter. The width of a pencil tip. The atoms near the top of that tiny cloud were 1 millimeter higher, a hair farther from the Earth than the atoms at the bottom. And that was enough. The top atoms ticked measurably faster than the bottom atoms. A pencil tip of height, and time itself ran at 2 different rates across it, and they caught it. The result came from 90 hours of patient data published in Nature, and it was about 50 times more precise than any measurement of its kind before. It points toward clocks 50 times better than today's best, clocks so sensitive that a step up a staircase would change their reading. Think about what that means for the picture in your head. Somewhere in that lattice, 1 strontium atom sits at the top and its twin sits at the bottom, perfectly identical, obeying exactly the same laws, and the one on top is aging faster than the one below, in a real and recorded sense, for no reason except that it floats a pencil tip closer to the sky. There is no universal now that both of them share. There is the top atom's time and the bottom atom's time, and they are not the same time. This is the thing to carry with you into sleep. There is no single clock for the universe. The moon gets a longer life because it moves. The satellite gets a faster tick because it is high. Your head ages a sliver ahead of your feet. The top of a cloud of atoms outruns its own bottom over 1 millimeter. Time is not a river that everyone is floating down together at the same speed. It is a rate, a local, personal, bendable rate, set by how fast you go and how deep in gravity you sit. And it is not a poetic way of speaking. It is a number corrected in orbit, machined into a crystal, printed in the datasheet of the machine in your pocket. Consider the clocks in orbit above you. Right now, roughly 12,000 miles overhead, a fleet of GPS satellites carries atomic clocks, and every one of them ticks a little faster than the identical clock would tick on the ground. The gap is small. It is about 38 millionths of a second each day. And that one tiny number is the reason the blue dot on your phone knows where you're standing. That 38 comes from two effects pulling against each other. A satellite moves fast, thousands of miles an hour, and motion slows a clock down. That is special relativity, and on its own it would lose the satellite about 7 microseconds a day. But the satellite also rides high above the Earth, far from the heavy pull of the ground, and weaker gravity lets a clock run quick. That is general relativity, and it adds about 45 microseconds a day. Take the 7 away from the 45 and you are left with 38, a net gain every single day for the life of the satellite. Engineers could not simply allow that, so before a satellite ever leaves the ground, they reach into its clock and detune it on purpose. The heartbeat is meant to sit at 1023 megahertz. They set it instead to about 10,002 to 299999943 megahertz. Slightly slow, deliberately, permanently wrong, down here where we can measure it. Then they launch it, and in orbit, with the speed and the thinner gravity doing their quiet work, that flat, mistuned clock is pulled back into perfect pitch. It is like slackening a guitar string on a cold morning, tuning it below the note on purpose, because you know the warmth of the room will stretch it up to true. The universe finishes the tuning for you. Leave that correction out, and the whole system unravels with startling speed. A GPS fix would drift into uselessness within about 2 minutes. After that, the errors keep stacking, roughly 6 miles of position error for every day it runs uncorrected. By the end of a week, the map would place you in the wrong town. The proof that time is personal is not resting in a textbook. It is baked into the hardware in your pocket, and it has to be, or the device would lie to you. These satellites catch time bending across thousands of miles of altitude. But the bending does not need thousands of miles. It does not even need an inch. In February 2022, physicists at JILA, a joint institute of the National Institute of Standards and Technology and the University of Colorado Boulder, measured the slowing of time across a single millimeter, 1 millimeter, about the width of a sharp pencil tip. They took a cloud of roughly 100,000 ultra-cold strontium atoms and cradled them in a lattice woven from laser light. Then they compared the atoms sitting at the top of that cloud with the atoms sitting at the bottom. The lower atoms rested a hair closer to the Earth, a hair deeper in its gravity, and so they ticked a shade slower than their twins, a millimeter higher up. Same atoms, same rule book, aging at measurably different rates, separated by less than the thickness of 2 stacked coins. That result was published in Nature on the 17th of February 2022. It came out of 90 hours of patient data. It was about 50 times more precise than any measurement of its kind before it, and it points the way toward clocks 50 times finer than the best ones we own today. Picture that upper atom and its lower twin, both flawless, both obedient to the same laws, and the higher one simply running ahead. Not as a metaphor, as a reading on an instrument. If satellites are too far away to feel, and single atoms too small to see, there is a third clock falling through you as you lie there. It rains down out of the sky. High in the atmosphere, roughly 6 to 9 miles up, cosmic rays crash into the air and shower down a spray of particles called muons. A muon is unstable. Left at rest, half of any batch decays in about 2.2 microseconds. That is its whole lifespan, and it is brutally short. At the speeds these muons travel, up to 0.994 times the speed of light, that clock says they should cover only about 2,000 feet before half of them are gone. 2,000 feet, and the ground is still miles below. By that arithmetic, almost none of them should ever reach you. And yet muons are the most common charged particle arriving at sea level. They pour through your body, through the floor, through the roof, in a steady, invisible drizzle. The reason is time dilation. Moving so near to light speed, their inner clocks run slow from where we stand, stretched by a factor of about 9. 9 times the lifespan measured from the ground, and suddenly those miles are easy to cross. This was not a guess. Bruno Rossi and David Hall pinned it down in a paper in Physical Review in 1941, counting muons at different altitudes and watching the survivors match the predicted stretch. It has since become such a clean demonstration that it runs as a routine student exercise, carried out every year in places like MIT's Junior Lab under the plain title of Measuring the Speed and Decay of Cosmic Ray Muons. Each muon that lands is a tiny borrowed sliver of extra time, handed to it by nothing more than its own speed. And you do not need an accelerator or the upper atmosphere or a lab full of lasers to catch the same thing happening. In the classic experiment run by Hafele and Keating, physicists simply bought seats on commercial airliners and brought atomic clocks along for the trip. They flew them around the world, once toward the east, once toward the west, and afterward compared them to twin clocks that had stayed behind, sitting still on the ground. The travelling clocks came home disagreeing with the ones that had stayed put, and they disagreed by very close to the precise amount relativity had predicted once you folded together the slowing from the aircraft's speed with the quickening from its altitude. Ordinary airplanes, ordinary flights on ordinary schedules, a measurable tear in the shared present carried home quietly in the luggage, so the evidence is not subtle and it is not rare. It sits in orbit, in a millimetre of laser light, in the soft rain of particles through your ceiling and in the cargo hold of a passenger jet. Every one of these clocks, tuned and flown and cooled and counted, tells you the same steady thing. Your time is your own. It runs at your speed and your height, and no other clock in the universe is under any obligation to agree with it. If the rate of time is this personal and this changeable, the next question is whether the laws themselves even know which way it is supposed to point. If the rate of time is this personal and this changeable, The next question is whether the laws themselves even know which way it is supposed to point. And here is the strange answer: they do not. Write down the fundamental equations of physics, and not one of them contains a built-in direction for time. Start with Newton. His laws of motion describe a ball, a planet, a swinging pendulum. Reverse the direction of time in those equations, and they still work perfectly. The motion you get is just as valid, just as physical, just as allowed. Maxwell's equations, the ones that govern every beam of light and every radio wave, behave the same way. Flip time, and light runs backward into its source, and the mathematics does not complain. The Schrodinger equation, the heart of quantum mechanics, is also symmetric under time reversal. So is Einstein's field equations, the description of gravity as curved space-time. 4 of the deepest theories we have, 4 pillars holding up all of modern physics, and every one of them is perfectly happy running the movie backward. Sit with that for a moment. Nothing in the core mathematics forbids a shattered cup from gathering itself off the floor. Nothing forbids heat flowing from cold to hot, or a puddle freezing itself back into an ice cube on a warm afternoon. The equations permit it. The universe simply never does it. You're watching the laws of physics fail to notice something you notice every second of your life. The laws are blind to the difference between yesterday and tomorrow. You are not. If you're enjoying following these strange corners of physics as you drift towards sleep, a like or a subscribe genuinely helps this channel keep making them. We are also on Spotify if you prefer to listen with your eyes closed. That is the only time I will ask. So the equations are symmetric. But is there anything, anywhere, in a laboratory that shows time itself has a preference? For a long time the answer was no. Then came 1964. That year, 2 physicists named James Cronin and Val Fitch were studying a strange particle called the neutral kaon. Kaons are unstable. They exist for a flicker, roughly a 10/1000th of a second, and then they decay into other particles. Cronin and Fitch were watching thousands of these decays, photographing them inside a detector at Brookhaven National Laboratory. What they found broke a rule that everyone had assumed was ironclad. In about 1 out of every 500 decays, the kaon violated something called CP symmetry. That is a combination of 2 mirror symmetries in physics. Almost every process respects it. The kaon, in a tiny fraction of cases, did not. 1 in 500. A rare defect buried in the decay of a particle that barely exists. It does not sound like much, but its consequences reach all the way down to the foundations. Here is why it matters for time. There is a principle in physics called the CPT theorem, and physicists treat it as close to sacred. It says that 3 symmetries taken together, charge, parity, and time reversal, must always be conserved as a package. If one of them is bent, another has to bend to keep the total intact. So if the kaon violates CP symmetry, the CPT theorem demands that it must also violate T, and T is time reversal. That is the whole point. This little defect in kaon decay is the closest thing anyone has ever caught to a fundamental asymmetry in time itself. a place where nature quietly distinguishes forward from backward at the smallest scale we can reach. Cronin and Fitch were given the Nobel Prize in Physics for it in 1980. That same faint asymmetry may be one of the reasons you exist at all. In the earliest universe, matter and antimatter should have been created in nearly equal amounts, and they should have annihilated each other completely, leaving nothing but light. Instead, a tiny imbalance survived, and everything you have ever touched is made of the leftovers. That imbalance and the kaon's broken symmetry are threads of the same story, and it is a detective story worth its own telling another night. For now, hold on to the shape of it. The laws are symmetric in time, but hidden in the decay of one obscure particle, in one case out of 500, nature seems to lean ever so slightly one way. And that lean is almost the only hint we have. The rest of physics still runs both directions with total indifference, which raises a genuinely disturbing possibility. Maybe forward is not a law, maybe forward is just an accident. To feel how strange that idea is, look at a phase of matter that was invented specifically to break time symmetries. The time crystal. An ordinary crystal, like salt or diamond, breaks symmetry in space. Its atoms lock into a repeating pattern, the same arrangement over and over, evenly spaced. In 2012, the Nobel laureate Frank Wilczek asked a wild question. Could matter do the same thing in time instead of space? Could a system settle into a state that repeats at fixed intervals in time, ticking forever, without any energy driving it, and without ever coming to rest? For years it was only a hypothesis. Many physicists thought it was impossible. A system at its lowest energy is supposed to sit still. That is what equilibrium means. A thing that oscillates forever sounds like a perpetual motion machine, and those are not allowed. Then, in 2016, it was actually built. 2 independent teams did it, one led by Mikhail Lukin at Harvard, the other by Christopher Monroe at the University of Maryland. Their results were published together in the same issue of the journal Nature in March of 2017. What they made is genuinely bizarre. A time crystal is matter that breaks time translation symmetry. It settles into a rhythm, flipping between states at a steady beat, and it keeps that beat indefinitely without settling down into stillness. An ordinary crystal repeats a pattern across space. A time crystal repeats a pattern across time. Picture it. A piece of matter that can never quite hold still. It oscillates between 2 states, back and forth, on and on, powered by nothing you could tap for energy, refusing the ordinary fate of every system, which is to run down and go quiet. It is a real, physical object that breaks the rules of time symmetry the way a snowflake breaks the rules of empty space. In 2021, Google used its Sycamore quantum processor to build one out of 20 qubits, hitting them with laser pulses so they flipped once for every 2 pulses, a rhythm half the speed of the drumbeat driving them. A crystal made of time, running inside a computer. None of this means we can reverse time, but it tells you something. Time's symmetries, the ones we treat as fixed features of the world, can be deliberately broken and rebuilt in a laboratory. They are more negotiable than they feel. Which brings us to the most unsettling recent work of all. The studies that ask directly whether the single direction we experience is written into the laws, or whether it is just the way the dice happen to fall. In February of 2025, two physicists at the University of Surrey, Andrea Rocco and Thomas Guff, published a result in the journal Scientific Reports. They were studying open quantum systems. Those are quantum systems that interact with their surroundings rather than sitting sealed off in perfect isolation, which is to say, systems like everything real. What they found, buried in the mathematics, was a hidden symmetry. The equations governing these systems contain a term they call a memory kernel, and that memory kernel turns out to be symmetric. In plain language, the math treats a backward arrow of time as exactly as valid as the forward one. Both were, in principle, equally possible. Read that carefully because it is a remarkable claim. According to their analysis, the direction time actually runs may not be forced on us by the laws. It may be a matter of statistical happenstance. The universe could just as easily have faced the other way, and the deep equations would not have known the difference. Their work suggests that the arrow you feel, the relentless one-way current carrying you from birth toward whatever comes next, might be less a law and more a coin that landed on one side. And yet the world still only runs one way, no matter how symmetric the mathematics underneath it turns out to be. Then came 2026, and the boldest step yet. In July of that year, physicists at Los Alamos National Laboratory published a study in the journal Physical Review X. The team, led by Luis Pedro Garcia Pintos, Yikai Liu, and Alexei Gorshkov, did not just find a symmetry in the equations, they used it. With a carefully engineered sequence of quantum measurements and feedback pulses, they steered a quantum system so that its trajectory appeared to run in reverse. They made its arrow of time look flipped. Let that land. Not a thought experiment. Not a simulation on a screen. A peer-reviewed result in which physicists took a real quantum system and coaxed it into behaving as though its own direction of time had been turned around. And in the same work they described something they call a measurement engine, a device that could pull usable energy directly out of the act of quantum measurement itself. We are a long way from reversing time in any world you can touch. This is a tiny, exquisitely controlled quantum setup, not a shattered cup reassembling on your kitchen floor. But the experiment reopens a question that will not go away. If the fundamental laws are indifferent to time's direction, and if a laboratory can engineer a system to run as though the arrow were flipped, then is forward really a law of physics at all? Step back and look at the whole landscape. Newton, Maxwell, Schrodinger, Einstein, all symmetric in time. One obscure particle, the kaon, leaning faintly one way in one decay out of 500. Time crystals that break time's symmetry on purpose. Equations whose hidden memory holds an opposite arrow as an equal possibility. And now a quantum system steered to run backward on command. Everywhere you press, the same answer keeps surfacing. The laws do not care which way time points. The caring, the direction, the forward, all of it seems to come from somewhere else. not from the equations, but from the peculiar, improbable state our universe started in, and the vast statistical drift that has followed ever since. You experience forward as the most solid fact there is. It is the frame every moment of your life hangs inside. But physics keeps whispering that forward might be a local accident, a feature of this universe, this history, this particular roll of the cosmic dice, rather than a rule stitched into reality itself. It is one thing to notice that the equations do not mind which way time runs. It is another to build a piece of matter that acts on that indifference. And in the last few years, that is exactly what physicists have learned to do. With tools you could almost picture in your hands. Start with the time crystal. The idea belongs to Frank Wilczek, who proposed it in 2012. He asked a simple question. An ordinary crystal breaks the smoothness of space. Its atoms lock into a repeating pattern, the same arrangement over and over, a grid that prefers certain positions to others. Could matter do the same thing with time? Could it lock into a rhythm that repeats at fixed intervals forever and never settle down into stillness? For years it was only a question on paper. Then, in 2016, 2 independent teams built one, and both results landed in the same issue of Nature in early 2017. One was led by Mikhail Lukin at Harvard, the other by Christopher Monroe at the University of Maryland. Different hardware, same strange behavior. Matter that ticks. The version worth picturing came in 2021 on Google's Sycamore processor. Here is roughly how the trick works. You take 20 qubits, 20 tiny quantum bits, each one able to hold a spin that points one way or the other. You line them up, then you hit them over and over with laser pulses, and you tune the whole system so that the spins do something an ordinary object would never do. They flip once for every 2 pulses. Sit with that number, because it is the heart of it. 2 taps of the driver, 1 flip of the spins. 2 more taps, 1 more flip. The system answers on every second beat and ignores the one in between. It is like a metronome that ticks only on the offbeat, patiently, forever, and never winds down, never drifts, never needs winding. The driver runs at one rhythm. The matter insists on running at half of it. That mismatch, that stubborn half time, is what it means to break the symmetry of time itself. The reason it holds, rather than smearing out into noise, is a phenomenon called many-body localization. Left alone, a system hit with that much energy should heat up, blur, and forget its rhythm. Many-body localization is what keeps it from heating. The disorder in the system traps the energy in place, so the qubits never cook themselves into a featureless soup. The Sycamore result was the first time crystal shown to be stabilized this way. Not a fluke that fades in a few beats, but a genuine phase of matter that keeps its offbeat pulse. Notice what this does not require. No fuel, no fresh push in a chosen direction. The pattern repeats in time the way wallpaper repeats in space, and it does so without settling into the quiet, unchanging equilibrium that everything else in nature drifts toward. That is why it unsettles people. It looks a little like a clock that keeps time out of nothing. Now take the second technique, which is newer and stranger, and points the other way. Not matter that keeps a rhythm, but a quantum system coaxed into running its own history backward. In 2026, 3 physicists at Los Alamos, Luis Pedro Garcia Pintos, Yikai Liu, and Alexei Gorshkov, published the recipe in Physical Review X. The ingredients are measurements and feedback pulses, arranged in a very particular order. And the order is everything. Here is the shape of it. A quantum system left to itself tends to drift along a certain statistical path. You watch it, you measure, but you do not measure passively. Each measurement tells you something about the state, and based on what it tells you, you fire back a feedback pulse, a small correction chosen to nudge the system one specific way. Then you measure again, nudge again, measure again. Step by careful step, the trajectory is steered so that it retraces itself. From the outside, it looks as though the system's arrow has been flipped, as though its private clock is running in reverse. It is not time travel. Nobody sends anything into the past. What the team engineered is a sequence of interventions so precisely timed and so tightly coupled that the system's apparent direction inverts. The reversal is real in the sense that it is measured and peer-reviewed. It is engineered in the sense that it takes a controller choosing each pulse in response to each reading. And there is a second gift buried in that same work, one that sounds almost impossible. They described a measurement engine. In ordinary life, measuring something is passive. You look, you learn, nothing moves. In quantum mechanics, the act of measurement changes the system, and that change carries energy. Their measurement engine is a scheme for extracting usable energy directly from the measurement process itself, not from heat, not from a battery, from the act of finding out, knowledge converted into work. Both of these techniques share a quiet lesson, and it is worth being careful about it, because it is easy to overstate. Neither one lets the past reach forward and change the present. They are built out of ordinary quantum mechanics, applied with extraordinary control, which brings us to the experiment people always reach for when they want to believe time can bend, the delayed choice quantum eraser. You may have heard it described in a thrilling way. A particle goes through an apparatus and behaves either as a wave or as a lump, and then, only afterward, a choice is made, and that later choice seems to reach back and decide how the particle already behaved before it was chosen. Cause following effect, the future editing the past. The concept traces to John Wheeler, who first imagined the delayed choice setup as a thought experiment, and it is genuinely beautiful. But here is how the trick actually works, and it is gentler than the headline. Nothing travels backward in time. The particles leave their record as they go. Every event is stamped and stored quietly as it happens. What comes later is not an influence, it is a sorting. You take the pile of recorded results, all of it already fixed, and you separate it into groups according to information gathered only at the end. When each group is laid out on its own, a clean pattern appears in it, a pattern that was invisible while everything sat mixed together. That sorting after the fact has a name. Physicists call it post-selection. Nothing that happened is being changed. You're only choosing which subset of what happened to look at, and the subsets were always there, waiting in the data. The wave pattern was never erased and never restored. It was hidden inside the full record and pulled out afterward by how the pages were filed. Picture a deck of cards dealt face down across a table, every card already printed, every value already settled. Later you turned them over and sort them into suits. The hearts were always hearts. You did not reach back and make them so by sorting. You only revealed an order that the dealing had already fixed. The delayed choice eraser is that sorting, dressed in the language of single particles, and the apparent magic lives entirely in the filing, not in the cards. So this is the honest picture of what the hands can do. You can build matter that keeps an offbeat rhythm forever, on 20 qubits, held steady by localization, ticking once for every 2 taps. You can steer a quantum trajectory into running backward, measurement by measurement, pulse by pulse, and even draw energy out of the looking. And you can take an experiment that seems to let the future rewrite the past and find, underneath it, nothing but careful bookkeeping and honest correlations. None of it breaks the rule you feel every waking hour, the one that carries you from morning to night and never the reverse. What all of it does instead is quietly loosen your grip on why that rule should exist at all. Every one of these techniques works because down at the level of the equations, the machinery genuinely does not know which way is forward. The forwardness has to be added by the world, by the setup, by the improbable low starting point everything unrolls from. In the bare mathematics, it is simply not there. And if forward is only the direction our particular universe happens to face, then perhaps the deepest equations of all do not point anywhere in time whatsoever. And if forward is only the direction our particular universe happens to face, then perhaps the deepest equations of all do not point anywhere in time whatsoever. This is not a poetic flourish. It is a technical result. When physicists tried to write the single equation that would govern absolutely everything, time quietly fell out of the math. It did not get demoted. It vanished. And nobody has fully explained where it went. The equation in question has a name. It is called the Wheeler-DeWitt equation, after John Wheeler and Bruce DeWitt, who assembled it across the 1960s and into the 1970s. They were chasing the great unfinished project of modern physics. They wanted to marry quantum mechanics, which rules the very small, to general relativity, which rules the very large. The prize was a single description that could hold both at once. What they produced was something stranger than either. The Wheeler-DeWitt equation does not describe a particle. It does not describe a planet. It describes a wave function of the entire universe. Every galaxy, every atom, every possible arrangement of everything, folded into one mathematical object. And when you look closely at that equation, you notice something is missing. There is no time variable in it. None. The letter that should stand for the passing of moments is simply not there. Here is the part that should stop you cold. In ordinary quantum mechanics, there is an operation you perform to ask how a system changes over time. You apply a mathematical object called the Hamiltonian. It tells you how the system evolves from one instant to the next. So the physicists applied the Hamiltonian to the wave function of the whole universe, expecting it to describe how the cosmos unfolds. The answer came back as exactly 0. Not a small number, not an approximate number, 0. The equation says in the cleanest possible language that the total wave function of the universe does not change. Nothing evolves. There is no ticking. At the deepest level physics can currently reach, the universe just is, entire and unmoving, like a single frozen photograph with no next frame waiting behind it. Before we go deeper into that stillness, one small thing. If a channel that treats physics this gently is what your night needs, a like or a subscribe genuinely helps these quiet documentaries find the next person lying awake. We're on Spotify too. That is the whole ask. Now let us return to a universe with no clock inside it. So you are left with a contradiction you can feel in your own chest. The equation says nothing changes, yet you are changing right now. Your heart is beating. The room is cooling. The night is moving toward morning. You are living proof that time passes, and the master equation of the cosmos says it does not. Physicists gave this contradiction a plain and slightly weary name. They call it the problem of time. It has sat largely unsolved for more than half a century. The problem of time is not a small footnote. It is the hinge on which quantum gravity turns. On one side, you have a timeless master equation, calm and total and still. On the other side, you have the lived universe, restless and evolving and full of before and after. Nobody knows for certain how to connect the two. How does a world of change grow out of a foundation with no when? That is the question. And every proposed answer is a story physicists tell about where time hides. The first story is the gentlest. Perhaps the universe has no outside clock, but it can carry a clock inside itself. Pick some real, physical quantity within the universe. Maybe the expansion of space. Maybe the value of some field spread through the cosmos. Then use that quantity as a stand-in for time. You do not measure the ticking of an external river. You measure one part of the universe against another, and you call that relationship the passage of time. Physicists call this an intrinsic clock. Time is not a background, it is a comparison. You already do this without thinking. You do not experience raw time. You experience the sun crossing the sky. You experience the sand falling in a glass. You experience the shadow lengthening on a wall. You have never once seen time itself. You have only ever seen one thing changing against another thing. The intrinsic clock idea takes that ordinary trick and makes it the whole basis of physics. There is no master river. There are only correlations, and you live inside one of them. The second story is subtler still, and it says that time is a thing that only appears when you stop looking too closely. Deep down, at the raw quantum gravitational level, the equations are timeless, but you do not live down there. You live in the wide, warm, classical world of tables and stars and weather. Physicists have a name for the bridge between those two worlds. They call it a semi-classical approximation. And in that approximation, when you zoom out from the smallest scales to the everyday, time quietly reappears. It was not there in the foundation. It emerges as you back away. Think of a photograph made of tiny dots of ink. Press your eye against the page and there is no face, only a scatter of specks with no order and no story. Step back across the room and a face swims into being, clear and whole. Nothing was added. You only changed your distance. Some physicists suspect time is like that face. It is not printed in the individual dots. It is what appears when you view the whole from far enough away. The third story is the most beautiful and the strangest, and it is where time turns out to be woven from something you have heard of. Its name is the thermal time hypothesis, and it comes from the physicist Carlo Rovelli working with the mathematician Alain Conner. It begins by accepting the hard truth. The universe as a whole is timeless. There is no cosmic river. But it does not stop there. It asks how flowing time could bubble up for a creature living inside a timeless whole. And the answer it gives is entanglement. Here is the picture. The universe is one vast, still, interconnected quantum state with no clock of its own. But its parts are entangled with one another, laced together in the deep quantum way. You are one of those parts. And because you are entangled with the rest, because you only ever see your own local corner and never the frozen whole, time flows for you. Your slice of the universe experiences a direction, a before and an after, precisely because it is a piece and not the totality. Time is not a thing the universe has. It is a thing that happens between its parts. The mathematics behind this is real, and it has a name too. The flow of time in this picture is derived using something called the Tomita-Takasaki theorem, applied to a system sitting in thermal equilibrium, a state physicists label with the letters KMS. In plain terms, a warm system in balance carries within its own statistics a natural sense of flow, and that flow is what we feel as the passing of time. Time and temperature turn out to be relatives. The same math ties this idea to the unhurried temperature, the strange prediction that an observer accelerating through empty space would feel that emptiness as a warm bath of particles. It ties it too to Hawking radiation, the faint glow that is expected to leak from the edge of a black hole. Heat and time braided together at the root. Sit with what that means for you. The reason your night moves forward in this view is not a law painted over the cosmos. It is that you are warm and you are apart, and you are entangled with everything you cannot see. Flow is what it feels like to be a fragment of a still and total thing. Your sense of tomorrow is the texture of your own incompleteness, and there is a fourth voice from one of the leading attempts to unify gravity and the quantum. It is called loop quantum gravity, and Carlo Rovelli stands near its center as well. In this theory, space itself is not smooth. It is grainy, built from tiny loops woven into a fabric. And background time, the steady outside river we all imagine, is treated as not fundamental. It is not part of the foundation. Rovelli says it plainly. The felt passage of time is closer to an emergent illusion. It arises from our limited, coarse-grained view, from the fact that we see the world blurred, in bulk, never grain by grain, see the fine detail and the flow dissolves. So notice where 4 different roads have led: the intrinsic clock, the semi-classical fade, the thermal time hypothesis, loop quantum gravity. They disagree about the mechanism, they quarrel about the math, but they arrive from 4 directions at the same unsettling doorstep. Time may not be a basic ingredient of reality. It may be something that leaks out of a deeper structure that has no time in it at all, the way warmth leaks out of the blind jostling of atoms that themselves have no temperature. And here is the wow beat to carry into the dark. Our most serious equations, the ones meant to describe the entire universe in a single stroke, may contain no when whatsoever. Apply the Hamiltonian, and the answer is 0. The cosmos, written in its truest language, may hold no moment marked now, no arrow, no tick. Yet the world still only runs one way for you, forward, unstoppably, night into morning. The equation is silent about time, and your life is nothing but time. Both of those are true at once, and no one has fully reconciled them. You do not need to resolve that tonight. Let it stay unfinished, the way it has stayed unfinished for the physicists themselves. There is a quiet comfort in it, if you let there be. The deepest description we have of everything is a kind of stillness, the motion, the passing, the sense of falling forward through your own hours might be the most personal thing about you, a flow that belongs to the part and not the whole. You are the place where a timeless universe learns, for a little while, how to feel time go by. And so the still equation leaves us at the edge of one more question, the one that has been waiting behind all the others. If time is not fundamental, if it emerges and can fade, then it did not always have to be. It could have a beginning. The universe, we are told, began, which means perhaps time began with it. And a thing that can begin is a thing that makes you wonder about its opposite end. I'll deliver the insert as raw narration. No file write tool is available in this insert task, and the hard rules specify raw narration only. None of these questions sits settled. Behind the tidy summaries, physicists are still arguing, and the arguments have names attached. Start with the beginning of everything. Roger Penrose looked at the ordered state the universe launched from and set its odds at about 1 in 10, raised to the power of 10, raised again to the power of 123. Try to feel the size of that. Suppose you took every particle in the observable universe, roughly 10 to the 92nd of them, and turned each single particle into a single printed 0. You would write zeros across every atom in every star in every galaxy, and you would still run out of room long before the number was finished. That is not the count of possible arrangements. That is only the length of the number that names their improbability. Penrose reached it by comparing volumes in what physicists call phase space. He measured the tiny region of starting conditions that could grow into the smooth universe we see, against the vastly larger space of conditions that would not. For decades, that figure has anchored the standard story. The cosmos began absurdly ordered, and everything since has been a slow drift into disorder. But in 2016, a Physical Review D-analysis pushed back, and pushed back hard. Its argument was simple and unsettling. Almost every starting state you could hand the cosmos expands. An expansion, all by itself, keeps opening fresh room for entropy to climb into. If that holds, then you may not need a wildly improbable first instant at all. The arrow could come from the stretching of space, not from some finely tuned seed. So the very foundation is in dispute. One camp calls the low entropy start the deepest fact in physics. The other calls it no real fact at all, just a habit shared by expanding universes. Nobody has closed that gap. Then there is the question of now. You feel the present as special, the one lit moment, the only stretch of time that is actually real. Relativity, read strictly, disagrees. In the block universe picture, past and future lie as fixed as any point marked on a map, and no single instant is privileged over the rest. Your birth and your death already sit inside that block, equally present, equally there. Time does not flow through it, any more than a road flows past a paper map lying still on a table. Against this stands presentism, the plain claim that only the present exists, that the past has already dissolved and the future has not yet been built. The physicist Julian Barber pressed that case to its edge in his 1999 book, The End of Time. He pointed at something you cannot easily shake off. You hold no evidence of the past except your memory of it, and that memory exists right now. You hold no evidence of the future except your present belief in it. Every record, every fossil, every old photograph is a thing that exists in this instant, and only this instant. Barber asked what survives if you take that fully seriously, and answered that time as you feel it flow might be an illusion from end to end. So picture two physicists standing in the same room. They hold the same equations and read them the same way, yet they part company completely. One insists that nothing has ever been more real than anything else, that the whole block simply is. The other insists that this single breath is all there has ever been. The mathematics on the page does not choose between them. Now step into the laboratory, where the argument turns sharp and physical. In 1964, James Cronin and Val Fitch ran an experiment at Brookhaven National Laboratory that has haunted the field ever since. They fired a beam of long-lived neutral kaons, particles labelled K-long, into a spark chamber, and they photographed the moments those particles fell apart. Across thousands of decays, each one unfolding in about a 10 billionth of a second, they caught something that should not have been there. Roughly one kaon in every 500 broke a symmetry called CP, the pairing of electric charge with mirror reflection. That result carries a hidden edge. Under the CPT theorem, one of the most trusted principles in all of physics, any violation of CP must also be a violation of T, of time reversal itself. So inside that spark chamber, in that one decay out of 500, nature revealed the faintest built-in preference for one direction of time over its reverse. It is the closest thing to true time asymmetry ever caught in a lab, and it helps explain why the universe holds so much more matter than antimatter. Cronin and Fitch took the Nobel Prize for it in 1980. Yet here the debate reopens rather than closes. Is that kaon asymmetry genuinely fundamental? A real tilt woven straight into the laws of nature? Or is it only a symptom, a shadow thrown by some deeper physics that nobody has found yet? The measurement itself is rock solid and has never been overturned. The meaning of it is anything but. A tilt buried in one obscure particle is a thin thread on which to hang the direction of all of time, and the physicists who study it know that better than anyone. And then comes the deepest fight of all, the argument over what should stand in for time once the very small and the very large are finally joined into one theory. One answer is the thermal time hypothesis, built by Carlo Rovelli and the mathematician Alain Connet. In their picture, the universe underneath is timeless, and time is a statistical thing, leaking out of our incomplete knowledge of the whole, the way warmth leaks out of countless jostling atoms. Time is never put in by hand. It emerges. The flow you feel is tied, in their mathematics, to the particular equilibrium state a system happens to sit in. A second answer comes from loop quantum gravity, the theory Rovelli helped construct. There, background time is stripped away as unreal from the start. The passage you sense gets described as an artifact of your own coarse and limited view, a blur left behind when you look at a fine underlying structure, too roughly to resolve its grain. A third answer lives inside string theory, which chases the same unification of gravity and the quantum world along an entirely different road, carrying its own assumptions about which pieces of reality are basic and which are merely derived from them. The trouble is that these three may not be describing one single truth from three different angles. They may simply disagree. Each offers its own resolution to what physicists openly call the problem of time, and those resolutions do not obviously fit together into anything whole. It is possible that at most one of them is right. It is possible that none of them is. What binds them is only the strangest feature they hold in common. When you sit down to write the one equation meant to govern the entire universe at once, the symbol for time keeps quietly falling out of it. An equation with no time inside it leaves one last question hanging in the dark. If time could begin, could it also end? An equation with no time inside it leaves one last question hanging in the dark. If time could begin, could it also end? You have followed time all the way down to its roots and found no flaw there, only stranger and stranger ground. So let your mind turn the other way now, toward the far future, and follow the same thread out to where it finally frays. Start with the matter around you, your hand, the wall, the water in the glass. Nearly everything you have ever touched is built from protons, and protons have always seemed permanent. But some theories predict even they slowly come undone. The estimates run enormous, somewhere between 10 to the 34th and 10 to the 40th years. Numbers like that are not really durations you can feel. They dwarf the current age of the universe so completely that 13.8 billion years becomes a rounding error, a single breath at the very start. Long after ordinary matter has thinned away, the black holes remain. They look eternal, and for a while they nearly are. But even they leak. Stephen Hawking showed that a black hole glows faintly at its edge, radiating itself away one particle at a time. A black hole the mass of the Sun would take something like 10 to the 67th years to vanish this way. The giants, the supermassive ones anchoring whole galaxies, hold on far longer, 10 to the 100th years or more. Picture that. An object that once swallowed entire stars, quietly evaporating into almost nothing, so slowly that the number describing it barely fits in the mind. And then, past 10 to the 100th years, there is the state physicists call heat death. Not fire, the opposite of fire. A universe spread so thin and so even that it becomes a dim, cold bath of faint photons and drifting neutrinos, the last scattered relics of everything that ever burned. No stars, no structure worth the name, no warm places and cold places for energy to flow between. Just a smooth, uniform hush stretched across a darkness with no edges. Here is the quiet part, the part worth carrying into sleep. The arrow of time, the thing that makes tomorrow different from yesterday, was never a law written into the equations. It runs on differences, on heat moving from warm to cold, on order sliding into disorder, on gradients that let something happen next. That is why the world still only runs one way. But in a true and complete heat death, those differences are gone. Nothing is hotter than anything else. Nothing can change, because there is nothing left to change into. Think about what that means for time itself. If nothing is changing anywhere, then there is no longer any operational difference between before and after. No clock can tick, because a clock is just something that changes in a countable way. No memory can form, because writing a memory takes an energy gradient to spend. In such a universe, asking how much time has passed becomes a question with no way to answer it and nothing to answer it about. The arrow does not so much stop as lose its meaning, the way a compass loses meaning at the exact centre of the earth. So hold the whole shape of it in your mind now, gently, the way you would hold something you do not need to solve. At one end, a beginning. Roughly 13.8 billion years ago, the universe emerging from the Planck epoch. That first, almost unthinkable sliver of about 10 to the minus 43rd of a second, the earliest moment our physics is even willing to describe. Time perhaps switching on there, or perhaps only becoming meaningful there, and at the other end, unfathomably far ahead, time possibly switching off again, not in a flash but in a fading, once the last black hole has evaporated and the last gradient has smoothed itself flat. Between those two horizons sits everything. Every sunrise, every conversation, every version of you that has ever been afraid of running out of time, all of it folded into a middle stretch so brief against those far numbers that the entire age of the cosmos so far is barely the first flicker of the reel. You live in the bright, busy, improbable early moments of a story whose ending is written in numbers no one can truly picture, and the strangeness that has followed you all night stays right to the end. Time may be the most ordinary thing you know, and also something that had a first instant and may have a last one, something our deepest equations cannot even find inside themselves. You do not have to resolve any of that tonight. Nobody has. The problem of time is still open, the beginning is still half in shadow, and the ending is only an estimate drawn on a scale that mocks the word soon. These are not worries to carry into the dark. They are more like the size of the sky above a campfire, something vast and quiet that makes the small warm circle you're sitting in feel gentler, not smaller. For now, none of those far numbers touch you. The night is ordinary. The clock beside you ticks at its steady human pace, the way it always has, the way it will in the morning. Time is still moving forward, one soft second after another, carrying you exactly where you are meant to go, which is toward rest. Let it. There is nothing here you need to hold on to, nothing you need to finish, nothing you need to understand before you close your eyes. The universe has been keeping time for 13.8 billion years without your help, and it will keep it a little longer while you sleep. So let the question settle. Let the numbers grow quiet. Let the one direction time still runs carry you gently down into rest. Sleep well tonight. Good night.